This is problem 2.4. Let us first go through the question. I will read it out for you. In the proposed laser interferometer space antenna or LISA gravity wave detection experiment, a laser beam of wavelength 1064 nanometers will be collimated with a telescope of diameter 30 centimeters and fired towards a satellite at a distance of 5 into 10 to the power 6 kilometers. Given that the power of the laser is 1 watt, estimate the power collected on the distant satellite through a telescope of the same diameter. You should note that this is a really high power laser, and for reference, the common laser pointers that we use for making presentations are less than 5 milliwatts in terms of its power. So in this LISA experiment, this really high power laser of 1 watt will be used. Before we proceed, let me draw a diagram for you to give you an idea of what the setup will look like. I'll grab hold of my pen. So we have the laser source over here. And this wavelength of 1064 nanometers laser is being used, which is much beyond the visible regime. Okay, my diagram is looking a little bit weird. Let me try and fix it. Much better. So what we have over here is this laser telescope. And then we have the satellite over here. And this distance between the telescope and the satellite is given to us. I'll call it L, which is 5 into 10 to the power 6 kilometers. And let's call this angle of divergence as theta. This angle is theta. And this radius here at the satellite, I will call it RF, F for final. Now from the circular diffraction pattern, we know that sine theta for diffraction pattern obtained from circular apertures or lenses is the following. Sine theta is 1.22 lambda over d. D is the diameter of the aperture or the lens being used. Here we are using a telescope of diameter 30 centimeters. So for us, d is 30 centimeters and lambda is given to us laser beam of wavelength 1064 nanometers. And since this angle will be very small, we can approximate sine theta as simply theta. We have used this approximation that sine theta is approximately theta for small angles. Now plugging in the values for this lambda and d and using my calculator, I get approximately 4.3 into 10 to the power minus 6 in radians. Now this radius at the satellite of this beam that is coming in, RF, will be L times theta again. This is coming from small angles because what we have is tan theta will be RF over L, which is approximately theta for small angles. This is again from the small angle approximation. So that gives us RF is L times theta. And this, when we put in the values, gives us approximately 2.1 into 10 to the power 4 meters. Now we need to find out the fraction collected, the fraction of the power collected at the satellite. That is what we need to find out. So that will be given as follows. So fraction of the power collected this will be equal to area of telescope aperture over the area of the original beam. So the beam size that is there at the satellite location, that is in the denominator, and area of the telescope aperture is in the numerator. So why we get this? This is because power is intensity over area. Intensity is power over area. So intensity equals power over area. So power is intensity times area. That means it is proportional to the area, and intensity of the beam is constant. It is what it is, the total intensity. Now we will put in these values. So area of the telescope aperture will be, telescope aperture we are given is diameter 30 centimeters, which we call as D. So area of telescope aperture is pi r squared, that means pi d by 2 squared, and area of beam, this beam upon expansion, is based on this RF. So that is pi times RF squared. So pi will cancel out. This gives us D over 2 times RF whole squared. And if we put in the values of D and RF, D from here, given RF we calculated. So putting in these values gives us approximately 4.8 into 10 to the power minus 11. So this is the fraction of power collected at the satellite, and we are given that initial power of the laser is 1 watt, which as I mentioned is really high. So final power will be equal to initial power times the fraction collected, and initial power 1 watt, fraction collected over here. So this gives us 4.8 into 10 to the power minus 11 watt, which is a very small fraction of the initial power. This completes problem 2.4.